Well, first of all, I want to thank all of you for staying with it all day and staying in the room. Appreciate that very much. And I want to confess that I just want to start off by saying every single generation talks about the next generation of manufacturing. So this title is terribly not creative. But we all went to I think a lot of us went to a really neat museum the other night. How many people, by show of hands, went to the Henry Ford Museum? Okay, so I'm going to start off with a quiz. And I'll let you out of this session if you pass the quiz. So, what drove the first industrial revolution? You don't need steam power. And the other night, if you were wandering around the museum, you would have seen this. This is a steam engine, steam power engine at the museum. What drove the second industrial revolution? Electrification. And if you were wandering around the museum, like Dale Brosius was, who I'm giving credit for all these brilliant photos, you would have seen this electric generator. What drove the third industrial revolution? IT. Now this picture is revealing for many reasons. That's right. That looks a lot like my first computer. That is the first Macintosh computer, and that looks a lot like the first computer I had and was very proud of. But absolutely that drove the third industrial revolution. So all these technologies, they did more than just drive industry and innovations there. They really changed behavior of people in society by enabling many, many things in society. So what about the fourth industrial revolution? What's going to drive that, you suppose? Of course, it's going to be the Internet of Things. So, steam power, if we go back to that first one, it transformed industry, but it did something else really interesting. It transformed mobility by harnessing energy. And by transforming mobility, it brought business together and created interconnectedness in ways that were never possible before. So the connectedness that steam power enabled was really unprecedented before steam power came into the scene. So again, Internet of Things is why we're here for the next few minutes to talk about maybe impacts on manufacturing. And the Internet of Things, which goes by a lot of names, the Industrial Internet of Things, the Internet of Everything, it's really about harnessing connectedness and what the various sources of data, for instance, in a manufacturing ecosystem, might bring, the value that data might bring, but not just the value that the data brings, but the value that acting on that data and the understanding that data brings. So we might extract and store data from a machine, from a process, think a unit operation in a manufacturing process. Then, of course, we have to understand that data, so we'll apply advanced machine learning, advanced analytics to that data. We then have to share that data with either people or machines, the right people, the right machines at the right time. And then, again, we have to act on it by feeding that back into our process, back into the development process, again, at the right time in the right place to add value to the organization. So it's about acquiring, analyzing, understanding, acting upon data from all sources. That includes simulation data. That includes measurement data. That includes subject matter data, opinion data. And so is that useful for the composite supply chain? So I think one of the ways in which to think about Internet of Things and how it might be useful is to think about how fast the composite supply chain wants to move, like in high volume manufacturing. I mean, what does it take to move fast, okay, while achieving cost targets? Well, I mean, you've got to move fast. You've got to achieve uniform flow, like in infusion and cure. And all these processes, in spite of variations that you might have, in material supply and in those processes. And so you're talking about going from processes on the order of 10 minutes to 1 minute. Data, if you can harness it quickly enough, and now Internet of Things technologies can enable that, can potentially make possible and help make possible the kinds of goals that high volume manufacturing has in mind in composites. So in terms of connectivity across the composites industry, we might think of it, for instance, starting with fiber production, courtesy of Oak Ridge National Laboratory, a place we've done quite a bit of experimentation on monitoring carbon fiber production process line, looking at and understanding what that tow experiences over the process line there at Oak Ridge National Laboratory, understanding preforming, using machine vision systems, understanding infusion systems, working with colleagues at University of Tennessee, Uday, and colleagues. But just taking the measurements is one thing, but understanding the measurements, of course, requires analytics, like edge detection techniques, deep learning techniques, right? That's what they call, by the way, in case you're not familiar with deep learning, that's what they call neural networks now. You always have to come up with new terms to make things that were old sound new. And it's not that deep learning isn't new and doesn't bring new things, but it's very much akin to neural networks. And what might it produce? It might produce really insightful results, for instance, on resin-rich areas in composite parts, like we see here in this basalt fiber composite sled that we manufactured with Uday's group. But one thing we know it produces is big data, because that data set right there, that infrared thermography data set alone was 22 gigabytes, right? Temporally, spatially, that's a lot of data. You agree? That's a lot of data. So, one of the questions we ask ourselves when we're out with our mobile laboratory trying to acquire data to help partners across IACMI is, how do we enable Internet of Things for manufacturing settings in a high volume manufacturing environment when all this data across sensors, models, and just measurements produce very high volume amounts of data? How do we do that? And I've shown you this before. And so forgive me for showing you it again. But this is, of course, the infamous infrared thermography on the phone system, the $200 infrared thermography system on the iPhone, detecting flaws in a composite laminate part. And what's important about this isn't that part, the non-destructive evaluation. What's important is that how do you manage these kinds of large data sets? Well, you already are on a connected, secure platform. It's already connected because that sensor is plugged into my iPhone. It's already secure because it's built on a platform that is an iOS system. The reason you don't have viruses in a Mac product is because they use a sandbox architecture for their iOS, right? You can infiltrate an app, but what's really hard to do in a Mac is getting outside that app. So if you ever have, and I've had viruses in apps, if you ever have an app, just reinstall the app. It's not a big deal. It's really hard to get a virus into an app in an Apple product and get outside that app. They trap you inside the app. And so it's a very connected and secure platform, the iOS system. So one idea relative to information technologies for Internet of Things is to already be on a connected and secure platform by having sensors plugged into devices like this. There is a pervasiveness of devices like that. Okay, so this is a curve that you always see. This shows billions of devices connected versus year. And just to give you a little bit of context, in 1994 I got my Bachelor of Science in engineering. And yes, we were evidently living in the information of technology Stone Age because we had a meager 1 million devices connected to the internet. When our students that entered this year graduate, they will have 50 billion devices connected to the internet. I mean, it's mind-blowing. Everything is connected to the internet. And so the power of that connectedness depends on, of course, our ability to harness the information that it produces. So, is this a hard thing to do? When I started doing my PhD work, it was really hard to connect sensors and measurements. I mean, I had to go buy proprietary systems and everything. And so now, right, I get my phone, right, and in seconds, I am on the Internet of Things. I can connect any sensor system to the Internet of Things. Yes, Bill, I can connect you and monitor you tonight at the auto show at the Internet of Things. Yes, I asked Kelly if she would do this, and she thought maybe with the government phone she shouldn't sign up for this. I got that on tape, Kelly. So the point of this isn't, oh, this is such a cool accelerometer, Doug. How can this be used for composites? But what if I plug an infrared into this? What if I have a vision system, right, plugged into a chip that's on the internet? All of those things are very easy. It's the ease with which you can connect. And then it's the engine for analytics. I encourage you to go try the Watson Internet of Things platform. They let you just experiment with all of the analytics. It's so easy to do Bayesian statistics. You feel like, you know how to do it, right? I'm a department chair, and I always say you got to make it easy enough for a department chair to understand it. And so it's a really exciting time to be looking at data and understanding how to use it. So how does IACMI approach this? I mean, you've seen this chart. It's such a great chart. Uday shows it, I think, in a number of his presentations. So the connectedness of materials and processes to manufacturing, design, and simulation models, to manufacturing platforms. And what do I see when I look at all these things? I see sensors, models, data. I see opportunity for drawing data, insight, feeding that insight back into processes. Some examples of things that are already going on, our colleagues from Purdue University who gave a session earlier today can tell you about how they're understanding the flow of short fibers through compression molding. Where do those fibers go? What orientation do they take in the process? How can they understand process property relationships a priori using physics-based simulation models and draping simulation models? And again, the connectedness of the simulation platforms is very important and is technical work. And then on top of that, it's now you can have access to this on your phone, right, through the internet. And so it's kind of like my demo with the Watson platform, right? It's the ease with which you can access these. It's great to have these excellent simulations, but if you can't use them, if you can't access them, they're not nearly as great. And so it's about making them accessible, and they've done both of those things. So it falls into the Internet of Things paradigm. And again, they've done that by combining all these tools, working with the partners across IACMI, not just combining the simulation tools, but validating those tools. And what do I see when I look at all those pieces of hardware? I see more data, right, coming off of those platforms that's being used to validate those simulation models. Other examples of connectivity in IACMI include the scaling up facilities. Many of us are going to go see the Scale Up facility and all the cool things that Ray and Larry and company are doing out there at their facility. And so an example of the sorts of things that are happening across IACMI, working, for instance, going from our laboratory where we build these little coupons to just understand, okay, a particular type of resin and curing phenomena in that resin. Understanding how to take that knowledge and work then with colleagues out at the Comet facility out in Denver, in Golden, and combining that knowledge across those scales. And so we have that across the range, as you know, of facilities. And again, what do I see? I see the industrial Internet of Things. And so if we combine these things, if we combine the simulation models that I talked about, for things like draping, with machine vision systems, edge detection, analytics to do preform, detection of flaws, correction of flaws in real time, with infusion systems, looking at flow, wetting, and other phenomena, coupled with cure monitoring, looking for resin-rich, resin-depleted areas in final composite parts. The idea is to not just acquire this data, but use it to inform processes. And that's really the idea of bringing together the Internet of Things. And I think an example of where data is being harnessed, we just met today as a project team, data is being harnessed in all these interesting ways. The team, Dave Snowberg and company, and Derek are leading in this with 11 industry partners on the thermoplastic project for wind turbine blade manufacturing, where they're bringing together, and you saw this great demonstration out in Denver just a couple years ago around this technology. So one last example, and then I'm going to close with one thought. Again, data is important, but it's not the end result. The end result is information that you can use to make decisions that maybe you can't make now. So we talk about energy consumption, embodied energy being one of those things that IACMI cares about. Here's an interesting example of understanding embodied energy in injection molding processes that a colleague of mine works on with NIST. And so in an injection molding process, you have different processes associated with this injection molding system. You have the melting, the injection process, the cooling process, all of which are governed by their own physics. And so what my colleague has done is he's used physics to model, for instance, melting processes and injection processes like flow and actual, decrystallization processes. But then data analytics, Bayesian networks, they're called Bayes networks, to model the cooling process. And what he's been able to capture as a result is a very accurate way to estimate the density of these parts using only the measurements that come off of these injection molding machines, just a few temperature measurements and a flow measurement. But not just an estimate of the mean density, but the distribution function, the probability, the uncertainty in the density. And that's what this is showing. This is showing a probability density function of the density of those parts, just from the measurements that are made. You can't make this measurement in the process, but you can estimate it if you think Internet of Things and combining the measurements of all those processes with simulation models. So taking you back to the beginning, as we were thinking about the Ford Museum and those great pictures Dale took, the four industrial revolutions, steam, electrification, information technology, all of which changed, I think, the face of industry, advanced industry, but also changed our behavior. Internet of Things very much has, and we're already, many would argue, consultants would argue, especially the ones that rely on business Internet of Things, let's just be honest, they would argue that we're already in that revolution, and it's about acquiring, analyzing, understanding, and acting upon the data to enable, for instance, high volume manufacturing of composites as a potential outcome. So, what I'd like to show you now is something as a takeaway. So tonight we're going to go to the auto show. And obviously we're all thinking about composites manufacturing, but we're going to be like sitting in cool cars. And so I was trying to think about how I could connect what's happening to that. And so it dawned on me that the Internet of Things is all around us. And what's interesting to me about the Internet of Things in manufacturing is that it's a real synergy between potentially how we make cars, right? The manufacturing technologies like machine vision and data analytics, and the technology we're putting in cars. And there's a synergy between those two things. So I'm going to show you my dad's car. And so this is a Tesla Model X. And this is me not driving my dad's Tesla Model X with a soundtrack, because it's better that way. So it's going to detect, you can see right there, it's going to detect right there, just detected that van. This is the steering, this is the auto steering function of my dad's car. Now it's going to detect that I'm not going the speed limit, but the car just went by, so now it can change lanes, and it does that by itself. And now it'll get back up Okay, now it's only going 65. It'll get back over to the right lane and it'll get back up to the speed limit. There. It detects all that automatically. Now, yes, it's going to park itself. And the first time this happened, I was terrified. I was like, Dad, are you sure? He was like, yes, trust it. Trust it. And then the wheel just flips out. And yes, the music is coming. So, 28 sensors, radar, ultrasonic, video, full field video around the vehicle, an onboard computer that is like 1,000,000 times faster than that Mac that I showed you. I mean, it parks really well. So, I think that's really cool. It's amazing. I would love to be a person that could, like John Williams, that could write great music for movies. I know, I understand who it is. I understand who it is, but John Williams has inspired more people than probably Strauss has. Okay, but the thing I wanted to point out, thank you for playing, the thing I want to point out is if I think back to the very first internship I ever had, it was to work on this car. So shout out to my alma mater, the Bearcats, University of Cincinnati. I worked on the GM EV1, the first commercial electric vehicle. It was so much fun. I would have never imagined like driving that car that I just showed you back in the day based on my experience working on that vehicle. But what breakthroughs occurred there, right, obviously inspired the breakthroughs that are happening now. And again, the thing that's interesting to me about Internet of Things is how it's permeating every aspect of our lives, from mobility to potentially manufacturing. And I think it's just starting to really make its way into the manufacturing environment. So that's what I have. I hope that was interesting. Not nearly as interesting, I know, as the auto show, but I want to tell you something else. All the people within IACMI, Robin said, who wants to go last at the IACMI members meeting? Who wants to go last? And I like raised my hand. I said, I want to go last. It's the best spot in the whole show, right, Uday? Remember that? Exactly. No, actually, I drew the short straw. And, but that's okay, because I really appreciate everybody sticking around. I really appreciate your time and attention, and encourage any discussion that we might have now. Look forward to seeing you at the show tonight. Thank you very much. Yeah.
As General Electric, where we make a composite fan blade, the only fan blade in the industry, we're using IoT for low volume, high quality parts.
Yeah.
Where today we have 99% yield, first time yield on a composite fan blade.
Okay.
So we've been tracking this field for quite some time. The challenge always is how do you convert that knowledge, feed it back into the manufacturing floor,
Right.
and have the process engineer make the change that you need.
Right.
So just want to say the application for low volume, high quality is as important as high volume.
Absolutely. So other applications outside of high volume speed. And by the way, any time somebody says high quality, that's music to my ears, you know, because I want to be all about quality and NDE supporting that. So yeah, thank you. Great point. Yeah. Yeah. So it's time to go enjoy the show, isn't it? Yeah. Any other questions? Oh yeah, sure. Brent.
You talk about the analysis. Obviously, data collection is much easier than analysis. Is the analysis really going to be...
Sorry, go ahead.
Is it really going to be a human function, or is the analysis going to become ever more automated, and who's going to make the decisions if that's the case?
Wow. I need a drink, like the question yesterday that somebody asked me. So I don't know if I can answer that question, but here's one way to frame maybe the way I'm thinking about your question, which is to say, I don't really distinguish between like the measurement, the analytics, and the simulation, because to me, all of those things are necessary to understand what the process is doing. So I'll give you an example. So if we're looking at, for instance, understanding what's happening in a polymer as it cures, we can make a temperature measurement. We can make a very sophisticated temperature measurement, but we need a model to understand what's happening inside the material, because we can really only make easily temperature measurements on the surface of the material, like the mold, let's say. And so what we need to be able to do is always move easily between all of those parts of our kind of Internet of Things. And so, you know, as an example, you know, we've been working on this project where, you know, we build kind of state awareness systems for temperature, state estimation, and flaw identification. And you know, the thing that I'm thinking of when you talk about, you know, moving between measurements and analysis is that there is no measurement, there is no direct measurement. You can't even really make a temperature measurement, you know. Usually you're making a resistance measurement, you're making an optical measurement, you're really inferring what the temperature is, right? And so there's always interpretation to be done. So I think, and the reason I want to frame it that way is because I think if you frame it in silos, I think you're doomed from almost the beginning. From a standpoint of this, then you've got siloed groups, and this has been my experience, by the way. You've got groups that are working independently, and then you're right. And then it's like who's sort of making the call, because you've got all these groups and they're all doing something different and they're not integrated from the get-go. And I would, I guess, advocate for a more integrated approach, and that's one of the things I really appreciate about IACMI is that it's taking that kind of integrated approach. And I think if you don't, you end up with a bunch of kind of cool stuff, but that's not integrated in the end. And it's like we were talking about in a members meeting today about a project. This is about solutions, you know. It's not about cool ideas. It's about solutions. So again, I wanted to frame it that way for that. Does that make sense, what I'm trying to say? Okay, because see, whenever I can't answer a question, I'm like a, excuse me, politician. I just answer the question I want to answer. Yes?
So along with the third wave, you know, the computers, Postman's paper on what he would do, create a lot of leisure time and increase quality of life. Could you please elaborate on the Internet of Things, what is expected to do to those elements that are valuable and treasures to the quality of life?
Wow, that is such a fascinating question. I would love for you to join Cliff and I tonight and just walk around the auto show and talk about this. Okay, so I have one thought about this. Her question is, and I really think this is true, you know, the Industrial Revolution, steam power, electrification, I mean, you couldn't read like at night without like, you know, kerosene lamps before electrification. That was like one of the more important things that ever happened, okay? But they did more than just spawn advances in industry, they changed behavior. So what might it enable in terms of changing in behavior that would improve our quality of life? So I have a colleague that does studies for Department of Energy on adoption of sustainable technologies, electric autonomous vehicles, okay? And he did a really cool study. And it was like around the state of California. And the study went like this. What would an autonomous vehicle enable, you know, for a community in the state of California? Imagine yourself now. What are the constraints that are imposed on you by having to drive your car? Well, what do you tend to do? You tend to buy a house that's someplace close to where you work. Why do you do that? Because you hate being in traffic, because it's stressful to like be in traffic, right? So you tend to live closer to where you work, right? Number one. So what would happen if the vehicles were autonomous, okay? More people would get to work faster, because autonomous fleets are actually much faster. People don't believe this, but even though the vehicles go slower, like I was talking to my friends at Local Motors today, they go slower, but it's much higher throughput. It's a traffic thing. No waves, no stop and go waves with autonomous vehicles. So what's interesting is that you'd think this is all good, right? This affects your quality of life. You could do work on the way to work. You could make calls. You could talk to your, brother or sister. Or watch Netflix, like Dale. Dale chooses other options. Thank you, Dale. Thank you, Dale. So, but here's the thing. What are the unintended consequences? And here are some interesting aspects, like from an energy standpoint. What happens to your decision, your behavior, if autonomy is pervasive? Now, we're talking about 2 or 3% of vehicles now. We're talking, 85 deep penetration of autonomy into mobility. What happens now? What constrains you now? Now what do? You move out the perimeter, right? Urban sprawl. Now you live further away from work. You're much less constrained. What does that do to the amount of energy that it takes to get to work? So energy consumption goes up overall, over the fleet, right? So there are these interesting aspects of it enables significant improvements in quality of life, but there are these interesting unintended consequences. In other words, engineers with the very best intentions also can create interesting social dynamics. And this is another reason why we have to not work in silos. We have to work with sociologists and people that know these kinds of things so that we can appreciate, and people that do computer science, so we appreciate the Internet of Things and what it can do. Because, all I can do is hook my phone up to the Internet, and I think that's cool. But we need people that really understand all these different dimensions. So that's an example, I think, of what it could enable, quality of life, but we also have to think about, as we're doing that, what are the consequences, I think. Because it's not all, we got to think about the trade-offs. Does that make sense? Yeah. Anyway, yeah.
Doug, I wasn't going to go here, but since you...
Oh, I'm sorry. Can we go now?
Real quick. Since you mentioned, the social change,
Yeah.
Which is probably more significant than any of these technological milestones through the ages.
Probably.
Maybe I'll admit that they're ushered in or nurtured by those technological changes. And I'm thinking now about your comment related to energy to get to work. But if you look at emergy, the units of energy affecting all aspects of our life, in recycling and everything else, since all of the new and upcoming generation spend all of their time in video worlds and augmented reality, all of those energy costs going into sailboats and sailplanes and driving to the climbing site for the weekend and the latest high-tech carbon fiber road bike or time trials bike.
We like that, though.
All those are going away. All you have to do is just keep supplying that cheap device because the lifestyle has changed so dramatically. So there's your solution.
What's the solution?
The solution is you don't have to worry about the energy of driving to work. If they spend 4 hours driving to work, there's no other aspect of their daily life that uses energy except, a couple of watts an hour.
Oh, I see. So the rest is going down. Okay. Problem solved. Anything else? Well, appreciate everybody's interesting questions. And like I said, look forward to seeing the auto show tonight. Thanks very much.